All right. So those of you at home, here was the question that we had today. And the answer was that they come out looking like a half circle. And you'll see that answer as we do our notes today. And the notes today are called diffraction. And basically what we're looking at is we're looking at what happens when you send waves through a tiny opening. If you do that, maybe you've got your waves and they look like this, and each line would represent a crest of a wave. So it's like having your bird's eye view, you're looking down. These are where the crests of your waves are located, and they're heading to the right. And eventually they get to an opening, and it's a small opening. Yeah, this will go in your notes. And so what happened when these waves went through that tiny little opening and found their way out the other end is they bent an awful lot. Something like this. And the main thing we're going to be doing in our notes is we're going to compare this with what comes out of that tiny little opening when we increase the opening and when we decrease the wavelength. We scrunch those waves together, and we're going to see how that all changes. So the next step then is what happens if we make the wavelengths much closer together. And you'll have to draw a separate picture. But if we make the wavelengths much closer together, it looks a little bit different on the other end of this opening. And so what happens with this, if you remember from our picture there, when we have the wavelengths closer together and they come out the other end, we see the same basic picture. We still see kind of a half circle looking thing, but it isn't as bendy. It's not as round as the circle was. So instead of being really elongated, really bendy, what ends up happening is it's kind of moderately bendy. So it looks about the same. But if you were to compare the amount of curvature in the last example to this one, you'd notice that there's less curvature in the previous, less curvature in this example than in the other one. And so what we're observing here is that when you have waves that are closer together, they don't bend as easily when they go through an opening like this. And we'll organize these thoughts at the end. For right now, just make sure you get the drawings in there. And make sure you can tell that this one's less curvy than the last one. I'm glad I don't use real scientific terms. I'm sure there's a scientific way of saying they're very curvy. I guess diffraction is how waves bend, so I suppose that's what I should say. But yeah, so that's what's happening when we have wavelengths that are close together and wavelengths that are far apart going through a really narrow opening. Now the question is, what happens if we change the opening? Now we've got a bigger opening. Maybe not quite that big. Maybe something like this. That'll do. And we'll go back to our original wavelength here. And so you'll draw this one separately again too. So when these waves went through that tiny little opening there, we observed the bending, and this one bent less than the first one we did, the one where these waves were far apart like this, but when they were going through a small opening, we observed the bend to be more than what we're going to observe when this goes through the larger opening. The bend that we see here is going to roughly be on par with the last picture that we drew. Of course, the wavelengths are more spread out, but in terms of the overall bending and overall curving, those two are about the same. And so that's what we observe when we have that big opening with big wavelengths. So the final step was to decrease the size of these wavelengths and have these go through that bigger opening. And this was the last scenario that we looked at. And when this happens, anybody remind me what happened in terms of the bendiness? Was it the most bendy or least bendy? It's one of those two. Least bendy, absolutely. When you have a big opening and close together wavelengths, you're going to get a very small amount of bendiness, or a very small amount of diffraction. So it's still bending for sure, but not as much as anything we've seen. And so we're going to go ahead and organize our thoughts on this now. And you can write in your notes what I'm putting up here in red. All right. I'll let you finish writing that down, and we'll just fill this in. That'll help us figure out when things are going to be real curvy and when things aren't going to be quite so curvy. All right, so let's see if we can remember a little bit here. So the very first scenario, when we had the large wavelength and we had the smallest opening, think of it in terms of small, medium, and large. Was that a large amount of bendiness, a large amount of diffraction, or small, or somewhere in the middle? Does anybody remember? Absolutely. That is a large amount of diffraction. It's the biggest kind that we can have. The more bendiness you have, the more diffraction you have. They mean the same thing. Now, when we had the small wavelength and the small opening for our second one, our diffraction went down a little bit. It was still relatively large. We still had kind of a half circle, but it wasn't as elongated as this first example. So this is just medium. And the third example was the same. We had then a big wavelength and a big opening. That also gave us that medium amount of diffraction. Finally, the small wavelength, large opening. How much diffraction did that give us? Small, absolutely. There was still bendiness there, but not nearly as much as the other examples. So this is how you need to be able to organize this information. And basically what it comes down to is you're just looking at what kind of properties are going to cause your wave to be more bendy and less bendy. So would you say that a big wavelength corresponds to a lot of bendiness or not a lot of bendiness? Would you say a larger wavelength would correspond to a lot of diffraction, or would that discourage the wave from bending? Yeah, it's going to make it bend more, because every time we've got a large wavelength, we've got either a large amount of diffraction, or in this case, a medium amount of diffraction. And how about the opening? Does a bigger opening give you lots of diffraction, or not so much? Not so much, absolutely. So, in other words, if you want your wave to be really bendy, the bigger the wavelength, the better. And the smaller the opening, the better. If you want your wave to be less bendy and be resistant to that curvature, then you want your opening to be larger and you want your wavelengths to be smaller. And so that brings us to the very last part of the notes then. Knowing all that information, we should be able to kind of predict what was going to happen when we put that round rock in our example. So if we do that, and we've got these long wavelength waves, and they go past that rock, they reconnect relatively quickly. Because long wavelengths bend easier, and so they'll be able to reconnect easier after they go by this rock. So maybe something like this. And so then what you would have behind this rock right here, you can kind of think of that as a shadow region. It's the area where that wave is not going to be connected to the other end of it. And so because these long wavelengths bend easier, it's going to reconnect pretty quickly. The other end of that spectrum is if we have wavelengths very close together, they go by this rock. And because these close wavelengths don't bend as easily, it's going to take them a lot longer to reconnect. So maybe something like this. So you've got a much larger shadow region. I shouldn't have put those the same as the wave. I'm just going to color it in. So you've got a much larger shadow region when you're dealing with rocks and obstacles that have waves that are very close together coming up to them. And that's what you need to know about diffraction. Questions on any of this? Wonderful. I bet you guys can get the homework done before you leave.